Welcome to chapter 3, where we're going to learn about finite groups and subgroups. And to introduce us to two important ideas, we're going to start by working through example 1. If you haven't done so already, I would pause the video, just read example 1 and try to answer the question yourself before you watch me work through it. Okay, so now let's look at it together. In example 1, we are looking at the group U7, the group of units mod 7, and you can convince yourself that that group includes 1, 2, 3, 4, 5, and 6. And the binary operation, the operation in this group is multiplication modulo 7. The Cayley table, they were nice, and it's already filled out over here on the right, so we can use that to help us quickly find answers about multiplication in this group. They're asking us to do two things basically. They're asking us to choose several elements of U7 and to raise them to higher and higher power. So this is the first thing they're asking us to do, and then to look at the results and see if we can generalize something. And then the second thing they're asking us to do is to fill in the multiplication tables over here on the right, at the bottom right, and to look at those multiplication tables for some subsets for H1 that includes 1, 2, and 4, and H2 which includes 1 and 6. So we're going to do these one at a time. Let's just look at the first question. Let's take some of these elements and raise them to higher and higher powers and see what happens. Okay, let's take an element, 2. If we raise 2 to the first power, that's just 2. What happens if we raise 2 to the second power? So that is 2 times 2, that's 4, mod 7, sorry, that is still 4. Okay, so 2 squared is 4. What about 2 cubed? So 2 cubed, that is 8, but mod 7, that is 1. Okay, so we have 2 to the first is 2, 2 squared is 4, and then 2 cubed is equal to 1. So what is 2 to the fourth going to be? Well, if 2 cubed is 1, then 2 to the fourth is just going to be 2. And we could keep going and going and going, but we just go around in circles. So we may as well stop because we already know what's going to happen. It's just going to cycle through 2, 4, 1, 2, 4, 1, 2, 4, 1. So this is kind of important that we cycle back to our identity in the group right here. Okay, let's look at another element. Let's look at 3. 3 to the first power, that's 3. 3 squared, that is 9, but 9 mod 7, that's 2. And what about 3 cubed? 3 cubed is, well, it's 3 squared times 3, so that is 2 times 3. We can help ourselves a little bit here because we already computed 3 squared. So that's 2 times 3, and that is 6. Mod 7, still 6. Okay, what about 3 to the fourth? That is, well, let's see, 3 to the fourth is 3 times 3 cubed. 3 cubed we already have. 3 cubed was 6, and then we just multiply by another 3. So that is 3 times 6, which is 18, but mod 7, that gives us 4. Okay, this looks like a lot of work. Let's look at 3 to the fifth. 3 to the fifth, that is 3 times 4, since we know that 3 to the fourth is 4. 3 times 4 is 12, mod 7 is 5. Okay, and then we'll just keep going. 3 to the sixth, what is that? That's 3 times 5. That is 14, but we're going mod 7, so that is 1. So thank goodness we can stop here, because 3 to the 7th, that would be 3 times 1. We'd have 3, and we are cycling. We are starting over. So we can really stop right here when we again reach the identity. Okay, wonder if this is a pattern. Let's pick another element. Let's go with 4. What about 4? 4 to the first power is 4. 4 squared is 2. 4 cubed is, well, using the same reasoning as before, that's 2 times 4. And that is 8. Mod 7 is 1. Okay, we reached the identity. We can stop right here because we would just cycle through the same numbers again. So when you're looking at these 3 examples, when we can stop, it seems like we cycle through a few different elements in our group, but eventually we're reaching the identity, and then the whole cycle starts over. This will also happen when you're doing this with 5 and when you're doing this with 6. So this is interesting. So we can write down our observation. Eventually, if the powers are high enough, we return to the identity. Let's write that down. So eventually, and we didn't prove this, we're just observing it. Eventually, if powers are high enough, we return to the identity. So that is one thing that is happening right here. Let's we move on to our second question and fill in the Cayley tables for the sets H1 and the set H2. So you can actually copy all of those from our big Cayley table right here, because the operation is the same. So we have 1, 2, and 4 in our first column, and 1, 2, and 4 in our first row, because 1 is just the identity, so it's going to leave our elements alone. And then 2 times 2 is 4. 4 times 2 is 1. 2 times 4 is 1, and 4 times 4, that is 2. So that is happening when we are looking at the Cayley table for the set H1. And for the set H2, we're getting 1, 6, 6, and 1. So this is what's happening for H. This is what we call the set H2. What do you notice when you're looking at those Cayley tables? What do you observe about the entries in those Cayley tables? Well, we only did multiplication between 1, 2, and 4 for H1, and we only have 1, 2, and 4 as entries in our Cayley table. And when we just looked at 1 and 6, we only got 1 and 6 as entries in our Cayley table. So we actually have closure under our operation multiplication mod 7 for both of those sets. So it looks like, I'm going to write that down, note H1 and H2 are closed under our operation. It looks like they behave just like a group themselves. And that is in fact true. So H1 and H2 are groups in their own right. And since they come out of their subsets of this bigger group U7, we call them subgroups of U7. So we call them subgroups of U of 7. And you could quickly go through and verify that they are groups. So we have closure. We already talked about that. We have an identity. That is 1. We have inverses. You can go through and find the inverse for each one in each case. because you see right here 2 and 4 are inverses of each other, and in H2 1 is its own inverse and 6 is its own inverse. So you can observe that right there. And the associativity, that is inherited from our bigger group, U7. So this is great. We found these two subgroups of our group U7. Okay, that is all I wanted to do in this example. And in the next example, we're going to generalize some of these ideas into